All right, welcome back, class. This is part two of our review session for the midterm. And just to recap, we had finished off with week three from part one, and we were going through our concentration and dilution. And so we're going to go back to that. All right, and so we were talking about molarity. And just to refresh your memory, molarity is equal to moles of solute over liters of solution. I wanted to go through this particular example because this time, instead of given the moles and the liters, you're given the grams and the liters. And so it says 6.5 grams of sodium hydroxide was used to make 0.45 liters of solution. We want to know what is the molarity. And so the molarity is equal to moles of solute over liters of solution. The first thing we want to do is convert grams to moles. So 6.5 grams of sodium hydroxide, NaOH, times 1 mole of sodium hydroxide over 39.99 grams of sodium hydroxide. That gives you 0.16 moles of sodium hydroxide. We're going to take that number and divide it by 0.45 liters, and we get 0.36 molar. You can either use capital M for your unit or MOL slash L, okay, moles slash liters for your units. Okay, so I did want to point that one out. The next thing I wanted to point out is your equivalence, okay? Okay, so your equivalence, the number of moles of charges of 1 mole of solute contributes to a solution. So in other words, if we have 1 mole of Na plus, okay, because it has that plus 1 charge, it gives you 1 equivalent. 1 mole of calcium 2 plus is equal to 2 equivalents because it has that plus 2 charge, okay? So 1 mole is 1 equivalent for sodium plus, 1 mole is 2 equivalents for Ca2 plus. So let's look at an example. And it says the normal range for potassium ions in the blood is 3.5 to 5.0 milliequivalents per liter. Is the concentration of 5.0 times 10 to the negative fourth molar within the healthy range? So K plus, because it's just plus 1, it's 1 equivalent per mole. And so first thing we want to do is change the molarity to equivalents per liter. Okay, so 5.0 times 10 to the negative fourth moles of K plus over 1 liter. Okay, that's from molarity. Remember, molarity is moles per liter. So times 1 equivalent of K plus divided by 1 mole of K plus. Remember, that equality is based on the charge. The charge determines how many equivalents. So you get 5.0 times 10 to the negative 4 equivalents of K plus over a liter. So 5.0 times 10 to the negative 4 equivalents of K plus over a liter times 1 milliequivalent over 1 times 10 to the negative third equivalents. This is the equality that relates equivalents to milliequivalents. So you get 0.5 milliequivalents of K plus over a liter. So it's not within this range, and so it's below the healthy range. Okay. All right. So you have a couple examples there. Dilution is the next thing I want to talk about, which is V original times C original is equal to V final times C final, where V's, whether it be original or final, represents volume, and the C's represent the concentration, which is the molarity. So let's look at an example of this. So we have a 0.250 liter sample of a 5.00 molar glucose solution. It's diluted to 1.40 liters. Calculate the molarity of the final solution. So the original solution has a concentration of 5.00 molar and a volume of 0.250 liters. The final concentration is what we're looking for, but the final volume, 1.40 liters. And so you can rearrange your equation to solve for our final concentration. We're going to plug in the original volume, 0.250 liters, the original concentration, 5.00 molar, and divide it by the final volume, 1.40 liters. All of these numbers have three significant figures, so our final answer will have three significant figures as well, 0.893 molar. Okay? And so that is an example of a dilution problem. So let's go back to our week 3 information, and we have our gas laws that I want to go through. All right, so for the gas laws, there are different equations associated with each of the different gas laws. We have Boyle's law, P1 V1 is equal to P2 V2, where the P's represent the pressure, V's represent volume. Okay, and then there's an example of that one. And this one is simply you're rearranging equations and plugging in your values. The P1 and the V1 are always the first pressure and volume listed in the problem. The P2 and V2 are always the second pressure and volume that are listed in the problem. There's always going to be one variable that you're going to solve for. Okay. Gay-Lussac's law, that's the P1 over T1 is equal to P2 over T2, where again, the P1 and T1 first pressure and temperature listed, P2 and T2 the second pressure and temperature listed. When you're looking at the gas laws, one thing to note is that the temperatures must be in Kelvin anytime, sorry about that, anytime you're dealing with any of the gas laws, your temperature must be in Kelvin. And so if we look at this example, you see how these two temperatures are in Celsius. You do need to convert them to Kelvin. And so you would add 273 to each of these temperatures to change it to Kelvin. And you must do that first before you're plugging it into the equation. Okay. And then we have Charles's law. Let me turn my ringer off. There we go. Okay. We have Charles's law where we have V1 over T1 is equal to V2 over T2. V's represent volume, T's represent temperature, and keep in mind your temperatures must be in Kelvin before you do these calculations. Okay. We have Avogadro's law, V1 over N1 is V2 over N2, where the V's are your volume and N's are the number of moles. Okay. And then we have the combined gas law. We have P1 V1 over T1 is equal to P2 V2 over T2. The temperatures must be in Kelvin, and as far as the pressures and the volumes, the units must match in order for the units to cancel out. And so, if you look at this example, you see how the volumes are both in liters. The temperatures you're going to change to Kelvin, and your pressure is in atmospheres. So your final pressure would be in atmospheres. Okay, so you do want those units to cancel out. Okay. And then we have the ideal gas law, where we have PV is equal to nRT. For P is your pressure and it must be in atmospheres. V is your volume, it must be in liters. N is the number of moles. R is this gas constant, 0.0821. And there are 4 units for the gas constant, liter, atmospheres over moles Kelvin. And then the temperature must be in Kelvin. And then there's an example of that. Okay. And then a final example to help you out. So go through those practice problems, make sure that you understand the gas laws and that you are using the correct units. Okay. So I want to look at, I know we haven't gotten to week 4 yet. That begins on Monday, but I do want to look over the review for the resources for week 4, just to tell you what we're going over, okay, for that week. So the addition reaction to alkenes. So in this particular week, we are starting to look at organic chemistry. And so we're going to look at alkenes. We're going to look at the nomenclature for alkanes. We're going to look at the pH scale. So that's still dealing with general chemistry. Neutralizing acids and bases, that's still dealing with general chemistry. Preparing esters, we're back to organic chemistry. And the reactions of amines and amides, that's organic chemistry as well. Carboxylic acids and phenols of weak organic acids, that would be organic chemistry. Reactions of hydrocarbons, that would be organic chemistry. And so I do want to go over the pH scale. Okay. The rest of the information is things that you'll learn. You'll know how to do reactions, you'll know how to do naming. And so, if you have questions on those particular things, please let me know. But I do want to go through the pH scale and look at the slides for that. And so when we're talking about the pH scale, we're determining if a particular solution is acidic, basic, or neutral. And so there is what is called the concentration of H3O plus and the concentration of OH minus. When you have H3O plus in these square brackets, that represents the concentration of. And the same thing with right here, we have the OH minus in these square brackets that represents the concentration of. And so if H3O plus is greater, it's going to be acidic. If they're equal, it's going to be basic. If OH is greater, it's going to be, I'm sorry, if they're equal, it's neutral. And if OH is greater, it's going to be basic. Okay. So H3O plus determines acidity. If it's greater, OH minus determines basicity if it's greater, and if they're equal, then it's going to be neutral. The value for the concentrations, 1.1 times 10 to the negative 7, if they are both that value, then it's going to be neutral. If H3O plus is greater than that value, then it's going to be acidic. If it's less than that value, it's going to be basic. Okay. And so we have the equation for pH, where the pH is equal to the negative log of the H3O plus concentration. And the pH ranges from 0 to 14. If it's less than 7, it's acidic. If it's equal to 7, it's neutral. If it's greater than 7, it is basic. Okay. And then this is a chart that shows you different values for the different levels. And so let's look at an example here. We want to know what is the pH of an aqueous solution having an OH minus concentration of 6.3 times 10 to the negative 1 molar. And so the first thing we want to do is define the H3O plus concentration because the pH relates to that concentration. And so in order to do that, you're going to take H3O plus is equal to Kw, which is known as an equilibrium constant for water, divided by the concentration of OH minus, which was given in the problem. Kw has a value of 1.0 times 10 to the negative 14. That value doesn't change, okay? So we're going to divide that by 6.3 times 10 to the negative 1. We get 1.59 times 10 to the negative 14. So now we can take this value, plug it in here, and take the negative log, we get 13.8. And that is our pH value. With a value of 13.8, that tells us that this particular solution is basic because it is greater than 7. Right? And then this gives you some examples of different substances that we know and their pH values. All right. And so, what if we were given the pH now and we want to calculate the H3O plus concentration? And so, we would use this equation. Okay. And so, it's actually 10 to the power of negative pH. Just to let you know that that should be that power. So, we have a solution at a pH of 2.0. We want to know the H3O plus concentration. And so that's equal to 10 to the negative pH, or 10 to the negative 2. And so it'd be 0.01 for your concentration. All right? And then you're given an example that you can work out on your own. All right? And so as you're going through each week's resources to help you prepare for the midterm for next week, let me know if you have questions. I hope these two videos were helpful for you in preparing you for the midterm.